So the first panel discussant is Dr. Jim McKerrow, nodding there, who is director of the Center for Drug Discovery and Innovation in Parasitic Diseases at the University of California. And he's been briefed, his topic is how to innovate, kickstart new science, particularly chemical biology and pharmacology. That's his remit. And so, Jim, the first question I'd like to ask you is, we've heard about target-based screening, but my understanding in the antibiotic field is actually that pharmaceutical companies have moved much more to phenotypic-based screening. And, you know, what new technologies are we going to need in this area to deal with this, particularly, for example, in the area of helminths, which is one of your specific areas? Diane's covered the trypnosomatids adequately.
So if you ask me, should we be screening against molecular targets, such as some that Diane has presented, we've heard about a lot yesterday, or should we be moving into phenotypic screens, I'd say yes, meaning we should do both. So what are the challenges for now doing phenotypic screens? I think that if we look at the successes of the past decade as we transition from that discussion yesterday to our discussion today, certainly I would say one thing we don't need more of is screening. There are a lot of really good screening centers in the community around the world. We heard one explained in detail yesterday. In terms of phenotypic screens, there are now high throughput or at least high content screens for all of the neglected disease parasites. Some are more challenging than others. The first that I'm aware of that was developed was probably malaria, followed by Trypanosoma brucei. Trypanosoma brucei, of course, because that's an extracellular parasite, so much easier to put into a HTS assay using 384 or higher level plates. But as Alan intimated, some of the more challenging phenotypic screens have been against the helminth parasites, which we haven't really talked about here. And I don't think it's anti-religious to mention those in the kinetoplastid meeting. But those, as many of you know, if we're talking about the river blindness parasite Onchocerca or the lymphatic filariasis parasite Brugia malay, for example, or Rucheraria, or even the schistosome, we're talking about much larger organisms. We're not in the protozoan anymore. So the challenge has been, how do you develop a screen for larger organisms? And without going into detail, because this has been published, I think that those screens have now been developed through a very clever collaboration, and I think yesterday we heard about the importance of collaborations. Very clever collaboration between computational scientists and code writers and people in this neglected disease field. So I think I would hope to see more of that in the future as well.
Okay, thank you. So the other part of drug discovery, of course, is animal models of disease. Do you think we have appropriate animal models of disease in all areas? Question. And if so, which ones would you want to see improved?
I think we could all say no. But it would really depend upon the organism. And this was an issue that was brought up yesterday, I think, very appropriately. I think, first of all, there are some models of disease, and our center is very much involved in this. There are some models of disease which I really do think recapitulate human disease fairly well. Some of the schistosome parasite screens and in vivo models in mice are that way. With Trypanosoma cruzi, which we've talked about, I think the point was made yesterday by Lucio that there are very many strains of T. cruzi, and I will tell you from our experience that if you pick the right strain, you can recapitulate heart failure in the mouse. If you pick the wrong strain, all you get is a big liver. Or if you pick the wrong strain, all you get is a dead mouse. So there, it's very strain dependent. And then there are other situations, and again, I'll return to the world of helminths, for example, lymphatic filariasis, where unfortunately I do not think there are good animal models at all. They're only models of, quote, infection, where you inject worms into the peritoneum of gerds, and that's really not a recapitulation of human disease. All you're doing there is creating a little well in the peritoneum of an animal. So I think in answer to Alan's question, I think we would all, conclude that no, we're really missing a lot of important animal models which are key to drug development, but it's really dependent upon which parasite and which strain of parasite we're talking about.
Yeah, thank you. I mean, I take your point, particularly for the filarial worms, obtaining Onchocerca from human patients, having them excised, digested to release the worm, and then flown for drug testing, and they won't fit in a 96-well plate, let alone a 354 model, is obviously extremely challenging. And
may I just add that
Yeah, sure.
the animal model that we have looked at for Onchocerca is the cow, which does not fit very well in most animal care facilities.
Thank you very much. Okay, so moving on to pharmacology, pharmacological behavior. Those of you who are not scientific experts, what I mean is how a drug enters the body, how long it stays in the body, how it's broken down and excreted in the body. These are important parts of the drug discovery process. And actually, many drugs fail because of inadequate pharmacology. So should this be a priority research area in an academic environment as well as a pharmaceutical environment? And what new tools do you think we need there?
Right. I think that's a very important question, again, one which was raised yesterday as well. And Alan said I could go off on a slight tangent talking about this, but I think part of the theme of today's panel discussion is where are the bottlenecks? What are the tools that we need in the next decade to move this field forward? And I would say that although I feel pretty confident that there are a lot of good screening centers around, GSK, Novartis, Dundee, UCSF, Broad, I mean, there's so many. What we don't have is enough medicinal chemists to move hits to leads and to optimize leads, and that's pharmacology. In other words, when you're saying at some point, I have a compound which I think is effective against this parasite, I want to get a proof of principle in an animal model, well, then the question is, well, how often do you give it to the animal? What dose? Do you give it once a day, twice a day, 3 times a day, for a week, 3 days? Those are questions which you can only answer if you have enough DMPK information. And so I think on the one hand, we need someone to step forward to provide that information, and we're beginning to see where that can come from. I think that yesterday when there were mention of certain consortia, particularly with the help of the pharmaceutical industry, there are places where this can be done. There are certainly CROs, contract research organizations, which do this on a contractual basis. That is, add money, we'll do it.
Very expensive.
So that can be done. But once you begin to get that information, you now need to take this compound, which is efficacious, and make it drug-like. And that requires a lot of chemistry. And I think one of the things that we're missing today that I would hope to see more of in the next 10 years is more medicinal chemistry expertise in that area. The other thing I just wanted to mention was...
briefly, please.
Briefly. Was yesterday someone pointed out that maybe it isn't the lack of screening, but it's the quality of the libraries that go into the screening. I think that's really true. And yesterday I think we heard that at least in some cases pharmaceutical libraries are non-overlapping. I would also emphasize there are 2 other places in the next decade I think we should go if we're going to leave no stone unturned for drug development. One is natural products. We've heard a little bit about those. We've seen examples of them. But I will tell you, if you look at all of the drugs that we currently take, 60% of them had their origin in natural products. And if you think about the antibiotics you take for bacterial infections, they all end in mycin, right? They're all natural products. And I know why the pharmaceutical industry moved away from natural products in the last decade. We all know the reason for that. They're very complicated, they're very difficult to synthesize. But as Diane mentioned, a revolution in technology, there has been a revolution in natural products technology, where now with deep genome sequencing, there are other ways of synthesizing natural products, and I think our community needs to look at this. And there's another reason to do this. If you look around at endemic areas in the world for the diseases that we're interested in, where those endemic areas may be resource poor in some aspects, they have biologic diversity. And if we can show people in those areas that there are new drugs for diseases that affect their children that are coming from this type of biologic diversity, people will be much more prone to preserve that biologic diversity, whether it be a rainforest or a reef. And that will allow us then to interface with the environmental preservation movement and their funding agencies.
Thank you. I think that's very important that we can really engage with disease endemic countries in the area of natural product research. You know, the problem with natural products is also the law of diminishing returns for antibiotics, but many of these compounds have never been tested against the parasite system. So thank you for making that important point.